A state known for earthquakes, droughts, towering mountains, and some of the most productive farmland on Earth, is confronting a less visible problem, one that develops slowly, often without immediate signs, yet carries consequences that extend across agriculture, water management, transportation networks, and flood protection systems. While much attention has focused on rising seas and intensifying storms, another transformation has been unfolding at the same time. In parts of California, the land itself is moving downward. Why are some areas dropping year after year? Why have sections of critical flood control infrastructure lost elevation that engineers once depended upon? Why are communities, farms, and water systems facing greater flood risks even in places far from the coastline? And why does a process occurring deep underground have the potential to reshape the future of one of America's most important states? Scientists have spent years measuring changes in California's landscape, using satellites, GPS instruments, aerial surveys, and ground observations. Their findings reveal that land subsidence, the gradual sinking of the Earth's surface, is occurring across multiple regions. In some locations, the changes are measured in inches per year. In others, the cumulative decline has reached several feet. The consequences extend beyond simple changes in elevation. Every inch of sinking can alter drainage patterns, reduce flood protection, damage infrastructure, and amplify the effects of sea level rise. California's struggle with sinking land is not entirely new. Records stretching back decades show that subsidence has affected portions of the state for generations. Yet the scale and persistence observed in recent years have renewed concerns among water managers, farmers, engineers, and planners responsible for protecting millions of residents and vast economic assets. The most dramatic examples are found in the Central Valley, a massive agricultural region stretching approximately 450 miles, or more than 720 kilometers, through the heart of California. Often described as one of the world's most productive farming regions, the valley supplies a significant share of the fruits, vegetables, and nuts consumed across the United States and exported internationally. The Central Valley depends heavily on water. During wet years, rivers flowing from the Sierra Nevada mountains help replenish reservoirs, streams, and groundwater supplies. During droughts, however, farmers frequently turn to underground aquifers to sustain crops. Those aquifers act as enormous natural storage systems, containing water accumulated over thousands of years. Problems emerge when groundwater is withdrawn faster than nature can replace it. Aquifers are not simply vast underground lakes. Many consist of layers of sand, gravel, clay, and sediments deposited over long geological periods. Water occupies spaces between these materials. When large amounts of groundwater are pumped out, pressure within those spaces decreases. Fine-grained sediments begin compressing under the weight of the overlying ground. The result is subsidence. Unlike seasonal fluctuations in water levels, the compaction of certain sediment layers can become permanent. Once compressed, those underground materials often cannot fully rebound even if groundwater later returns. The storage capacity of the aquifer itself may be reduced, creating a long-term challenge for future water supplies. Measurements collected over recent decades have documented substantial sinking across portions of the San Joaquin Valley, the southern section of the Central Valley. In several areas, cumulative subsidence has reached remarkable levels. Some flood control structures and canals have experienced enough elevation loss to affect their intended operation. One of the most significant concerns involves levees. Levees serve as barriers designed to keep rivers and floodwaters contained within designated channels. Throughout California's agricultural regions, hundreds of miles of levees protect farmland, communities, roads, and infrastructure from inundation. Many of these structures were originally designed with specific elevations intended to withstand expected flood conditions. When the surrounding land sinks, the relative height and effectiveness of those defenses can diminish. Along portions of the San Joaquin River system, some levees have reportedly experienced sinking exceeding 6 feet, or approximately 1.8 meters. That amount of elevation loss can fundamentally alter flood risk calculations. Water that once remained safely below a levee crest may come closer to overtopping during periods of heavy runoff. The challenge is not limited to levees alone. California operates one of the most extensive water delivery systems in the world. Reservoirs, canals, pumping stations, aqueducts, and distribution networks move water across vast distances to support cities, industries, and agriculture. Many components of that system depend on gravity. Canals are carefully engineered with precise slopes that allow water to flow efficiently from one location to another. Subsidence can disrupt those gradients. If one section sinks more rapidly than another, water movement may slow, pool, or require costly engineering modifications. Several major canals crossing the Central Valley have experienced subsidence-related impacts over the years. Reduced carrying capacity has forced agencies to undertake repairs, redesigns, and operational adjustments. In some locations, sections of infrastructure required raising or reconstruction to restore intended performance. The financial implications are substantial. Repairing infrastructure affected by sinking land can cost hundreds of millions of dollars. Maintaining flood protection, restoring water conveyance capacity, and adapting transportation systems all require long-term investments. Roads and bridges face challenges as well. When land subsides unevenly, pavement can crack, road surfaces may distort, and structural stresses can increase. Rail lines can experience alignment issues. Drainage systems designed for historical elevations may lose effectiveness. The consequences often develop gradually, making them less visible than dramatic natural disasters. Yet over time, the cumulative impacts become increasingly difficult to ignore. Satellite technology has transformed scientists' ability to monitor these changes. Radar instruments orbiting hundreds of miles above Earth can detect minute shifts in land elevation. Using a technique known as interferometric synthetic aperture radar, researchers compare satellite observations collected over different periods to identify subtle vertical movements. These measurements reveal patterns that would otherwise remain hidden. Across portions of California, satellite data show a patchwork landscape where some areas remain relatively stable while others continue sinking. The differences often reflect local geology, groundwater use, land management practices, and historical development patterns. GPS monitoring networks provide additional confirmation. Highly precise instruments anchored to the ground can measure movement with extraordinary accuracy. Combined with satellite observations, these systems help scientists map regions experiencing uplift, stability, or subsidence. The findings extend beyond the agricultural interior. Parts of the San Francisco Bay region have experienced measurable land subsidence. Similar patterns have been identified in portions of the Los Angeles area and around San Diego. The causes vary by location, reflecting different geological and human influences. Groundwater extraction remains one of the most significant drivers in many regions. Urban growth increases demand for water. Agricultural operations require reliable supplies during dry periods. Extended droughts often intensify pumping as surface water availability declines. California has experienced several severe drought episodes during the past decades. During those periods, groundwater withdrawal increased dramatically in some regions, accelerating subsidence rates. Natural geological processes also contribute. California sits along a complex network of faults and tectonic boundaries. The interaction of Earth's crustal plates produces continuous, though often imperceptible, movement. Some locations rise while others sink due to long-term geological forces. Sediment settling can play a role as well. Coastal and river delta environments naturally compact over time as accumulated sediments adjust under their own weight. Human development, drainage modifications, and alterations to natural water flow can influence these processes. Oil and gas extraction has historically contributed to subsidence in certain areas. Removing fluids from underground reservoirs can alter pressure conditions and lead to localized sinking. Similar effects have been documented in oil-producing regions around the world. Although the causes differ, the result remains the same: lower ground elevations and increased vulnerability to flooding. Flood risk is often viewed primarily through the lens of weather. Heavy rain, river overflow, snowmelt, storm surge, and hurricanes typically dominate public discussion. Yet elevation plays an equally critical role. A community situated several feet lower than before may face entirely different flood dynamics even if rainfall totals remain unchanged. Water follows gravity. As land subsides, drainage pathways can shift. Areas that once drained efficiently may become prone to ponding and prolonged inundation. Floodwaters may spread farther across low-lying landscapes. Pumping systems may need upgrades to compensate for altered elevations. In agricultural regions, the consequences can be especially significant. Flooded fields can damage crops, delay planting schedules, and disrupt harvest operations. Standing water may persist longer in depressed areas created by uneven subsidence. Transportation routes used to move agricultural products can become more vulnerable to flooding events. The relationship between subsidence and flood risk becomes even more concerning when combined with climate-related changes. California's weather has historically alternated between drought and intense precipitation. Atmospheric rivers, long corridors of concentrated moisture, can deliver enormous quantities of rain and mountain snowfall. Recent years have demonstrated the destructive potential of these events. When powerful storms strike landscapes already experiencing subsidence, flood control systems face additional pressure. Lower ground elevations reduce safety margins that engineers may have relied upon when designing infrastructure decades earlier. Coastal regions face a different, but equally serious challenge. Global sea levels have been rising as ocean waters expand due to warming temperatures, and land-based ice contributes additional water to the oceans. While sea level rise receives significant attention, local land movement can dramatically alter its effects. Relative sea level rise represents the combined influence of ocean changes and land elevation changes. Imagine a coastline where the sea rises by 3 feet, or approximately 0.9 meters. If the land simultaneously sinks by 1 foot, or approximately 0.3 meters, the practical effect resembles a 4-foot, or roughly 1.2 meter, increase in water level relative to the land. That combined impact is what concerns planners. Along portions of California's coastline, subsidence can intensify the effects of rising seas. Areas already vulnerable to tidal flooding may experience more frequent inundation. Storm surges can penetrate farther inland. Coastal drainage systems may become less effective. San Francisco Bay illustrates the complexity of the challenge. The Bay region contains extensive shorelines, wetlands, transportation infrastructure, residential neighborhoods, and commercial districts situated near sea level. Small changes in elevation can influence flood frequency and shoreline stability. In parts of the Los Angeles region, dense urban development intersects with coastal exposure. Subsidence, sea level rise, and population growth create overlapping pressures that require careful planning. San Diego faces similar considerations. Although local conditions vary considerably, the combination of sinking land and rising seas can alter flood projections used for future development decisions. Saltwater intrusion represents another concern. As sea levels rise and land elevations decline, saltwater can migrate farther inland through rivers, estuaries, and groundwater systems. Freshwater resources may become more difficult to manage. Agricultural operations dependent on high-quality water supplies can face additional challenges. Drainage infrastructure may encounter increasing strain. Stormwater systems rely on gravity to move water away from developed areas. Lower elevations can reduce efficiency and increase dependence on pumps and engineered solutions. The issue extends beyond major cities and famous coastlines. California contains numerous river systems, floodplains, wetlands, and delta regions, where even modest changes in elevation can influence water movement. The Sacramento-San Joaquin Delta represents one of the state's most strategically important landscapes. This intricate network of waterways plays a central role in California's water supply system. Many islands within the delta are protected by levees. Some areas already lie below surrounding water levels. Continued subsidence can increase the challenge of maintaining adequate flood protection. A levee failure in such environments can produce extensive flooding, disrupt transportation corridors, and affect water distribution networks serving millions of people. Historical records demonstrate that subsidence has been occurring in parts of California for decades. During the 20th century, sections of the San Joaquin Valley experienced some of the most dramatic land surface declines ever documented in the United States. Groundwater pumping associated with agricultural expansion contributed significantly to those changes. Efforts to improve water management have achieved varying degrees of success. Surface water projects reduced reliance on groundwater in certain periods, slowing subsidence rates in some locations. However, recurring droughts and ongoing demand have continued to place pressure on underground aquifers. Recognition of these challenges contributed to the development of groundwater management initiatives aimed at promoting long-term sustainability. The objective is straightforward in principle: balance groundwater withdrawals with replenishment over time. Achieving that balance is considerably more complex in practice. Water availability fluctuates dramatically between wet and dry years. Agricultural demands vary. Population growth continues. Climate conditions introduce additional uncertainty. Meanwhile, subsidence can continue even after pumping rates decline because geological responses may lag behind changes in water use. Scientists therefore monitor conditions continuously. Satellite observations provide broad regional coverage. GPS stations offer precise local measurements. Groundwater wells track changes in aquifer levels. Together, these tools create an increasingly detailed picture of California's evolving landscape. The data reveal that subsidence is not uniform. Some locations remain relatively stable. Others sink slowly. Certain areas experience substantially higher rates than neighboring regions only a short distance away. Geology helps explain many of these differences. Aquifers containing thick clay layers are often more susceptible to compaction. Areas with intensive groundwater extraction can exhibit stronger subsidence signals. Historical patterns of sediment deposition influence how underground materials respond to pressure changes. Understanding these local variations is essential for planning. Infrastructure designed for stable ground may require different approaches in areas experiencing ongoing subsidence. Flood protection projects must account for future elevation changes rather than relying solely on historical conditions. Long-term projections increasingly incorporate land movement alongside traditional flood risk assessments. For coastal communities, planners evaluate combinations of sea level rise, storm surge, tidal flooding, and subsidence. For inland regions, assessments may consider river flooding, levee performance, drainage capacity, and groundwater conditions. The challenge illustrates a broader reality about environmental change. Not all significant threats arrive in dramatic fashion. Some emerge gradually through the accumulation of small shifts over many years. A fraction of an inch lost annually may seem insignificant. Over decades, however, those losses can transform landscapes, alter infrastructure performance, and reshape flood risks. California's sinking land exemplifies that process. The state's future flood exposure will depend not only on rainfall, river flows, and ocean levels, but also on the stability of the ground itself. In portions of the Central Valley, subsidence has already reduced levee elevations and affected water delivery systems. Along parts of the coast, land movement compounds the challenges associated with rising seas. Across multiple regions, satellite and GPS observations continue documenting vertical changes that influence planning decisions. The warning emerging from these measurements is not centered on a single catastrophic event. It reflects the cumulative consequences of gradual elevation loss occurring across diverse landscapes. Lower ground means reduced margins of safety. Lower ground means greater exposure to high water. Lower ground means infrastructure designed for past conditions may face future stresses it was never intended to handle. California remains one of the world's leading centers of technology, agriculture, engineering, and scientific research. Yet even in a state renowned for innovation, geography still matters. Elevation matters. Water movement matters. The interaction between human activity, natural processes, and climate influences the risks communities face. For many years, drought dominated discussions about California's water future. Today, another reality is becoming increasingly difficult to overlook. In parts of the state, the land is slowly descending. Every inch lost changes the relationship between rivers and levees, coastlines and tides, infrastructure and floodwaters. The significance of that change lies not merely in the sinking itself, but in what follows afterward. As land levels continue to decline in vulnerable regions, flood risks grow, drainage challenges intensify, and the effects of rising seas become more pronounced. The result is a future in which the state's battle against water may depend as much on the elevation of the land beneath people's feet as on the water arriving from above. Another factor increasing concern is the pace at which some subsidence can occur during extended drought periods. While many people imagine land sinking as an extremely slow geological process measured only over centuries, observations from California demonstrate that meaningful changes can occur within a matter of years when groundwater extraction intensifies. In heavily pumped agricultural areas, land that appears stable at the surface may be undergoing gradual compression underground, producing measurable elevation losses that accumulate season after season. The implications reach beyond flood protection and water delivery. Subsidence can influence ecosystem health in wetlands, river corridors, and seasonal floodplains. Many habitats depend on specific water levels and drainage conditions. When elevations change, water may collect in different locations, remain longer than expected, or bypass areas that historically received seasonal flooding. Such alterations can affect vegetation patterns, wildlife habitat, and the natural functioning of aquatic environments. Emergency planning agencies are also paying increasing attention to elevation changes. Flood maps are among the most important tools used by local governments, developers, insurers, and residents. These maps help identify areas vulnerable to inundation during severe weather events. When land subsides, flood risk calculations may require updates, because the topography used in earlier assessments may no longer accurately represent present-day conditions. Areas once considered relatively secure can gradually become more exposed as ground elevations decline. Snowmelt presents another dimension of the challenge. California receives a substantial portion of its water supply from snow accumulated in the Sierra Nevada during winter. During warm periods, that snow melts and flows into rivers, reservoirs, and agricultural regions. Years featuring unusually large snowpacks can place additional pressure on flood control systems as runoff moves through the state's waterways. In regions where levees or channels have lost elevation due to subsidence, the capacity to safely manage large volumes of water may be reduced compared with original design expectations. Technological advances have significantly improved the ability to track these changes. Modern satellites can repeatedly scan the same locations and detect subtle shifts in elevation across enormous areas. This capability allows scientists to identify emerging hotspots of subsidence before major damage becomes apparent. The growing availability of detailed monitoring data provides decision-makers with a clearer understanding of where risks are increasing and where preventive measures may be needed. California's experience is also attracting attention beyond its borders. Land subsidence affects regions throughout the world, particularly areas dependent on groundwater. From agricultural basins to coastal cities, communities are confronting similar challenges involving sinking land, flood exposure, and water resource management. The lessons emerging from California illustrate the importance of understanding not only the movement of water across the landscape, but also the movement of the landscape itself.